Last but not least, we have our pancreas, and I went back to one of our beginning slides so we could identify where that is. So the pancreas is going to be hugging the stomach in the abdomen section, and the pancreas, we can see here in kind of that darker orange just on the inferior aspect of the stomach. And the pancreas has arguably some of the most important functions when it comes to the digestive system. So let's go back to those slides. All right, so here's a zoomed in picture of the pancreas, and we can see that the pancreas is just lateral to the duodenum, which is the first part of the small intestine. And the stomach, you can imagine, is just on the superior aspect of the pancreas. The pancreas is going to be retroperitoneal, and we'll talk about what retroperitoneal means whenever we really get to the digestive system chapter. But essentially, this means that it's behind the rest of the peritoneum. And the peritoneum is what is wrapping around most of the organs in the abdomen. This will make a lot more sense when we get to the digestive system chapter. Okay, the pancreas itself has both endocrine and exocrine functions. So we'll talk about the exocrine functions when we get to the digestive system. But here, since this is the endocrine chapter, this is where we'll introduce it. So even though the endocrine functions might seem like they're the most relevant and most, important perhaps for the pancreas, they only make up only 1% of the functionality of the pancreas. The rest are 99%, and that's just the exocrine functions. So when we're talking about the endocrine functions, we're talking about hormones, and we're talking about exocrine functions, we're talking about enzymes. And for the hormones, they get secreted directly into the bloodstream. So that's going to be with the majority of the cells that you can see make up the pancreas. Versus the enzymes are going to be made with the rest of the cells, and when those are secreted, they're going to be secreted into what we call the pancreatic duct, which you can see going right through the pancreas. And then that pancreatic duct empties into the small intestine, into the duodenum there. So here we can have a better visualization of what's going on. So this picture I pulled from another textbook, just because I think it gives you a better picture of what the pancreas really looks like on a microscopic level. So in the top right picture, you have the pancreas next to the stomach. And then the picture on the left, you can see the same view that we saw in the last slide. But here they took out a portion of the pancreatic cells so that you can see the pancreatic duct. And then they took some of those cells and they zoomed in on them. Goodness. And here we can see the pancreatic duct going through those cells in the bottom right picture. And surrounding those, we have the pancreatic cells. And each of these cells are going to be, or a majority of these cells are going to be creating those pancreatic enzymes, which are going to be secreted into the duct and down into the small intestine. And we're not going to talk about those for this chapter because, like I said, those will come up for the digestive system chapter. The rest of the cells, that 1%, are going to be called the islet of Langerhans, or the pancreatic islets. Islet of Langerhans is the older term. We don't use that anymore. Anatomy is trying to move away from using structures that are named after people, but rather actually naming them after what they're surrounding. So they're called the pancreatic islet cells. And those pancreatic islet cells are few and in between, but they're still there. And they are going to be made up of 3 different types of cells: an alpha cell, a beta cell, and a delta cell. And those cells are going to be creating those hormones, and then those hormones have to go dump into the bloodstream so that they can go and signal the rest of the cells that they need to as appropriate. And in order for them to be close to the bloodstream, we're going to have arteries and veins actually passing in and out of nearby these pancreatic cells, the pancreatic islets. So that's why I picked this picture, because I think it kind of gives you a better orientation of what's going on. Now let's talk a little bit more in detail about what each of those cells are doing. So we have the alpha, the beta, and the delta cells. And the alpha cells are releasing glucagon. The beta cells are releasing insulin. The delta cells are releasing growth-inhibiting hormone. And we have some additional cells called PP cells, which are usually in the islets, not always in the islets. But these are pancreatic polypeptide hormones, and they are going to help the gallbladder know when to stop contracting. We don't talk about it much for the purposes of this course. It might come up again during the digestive system chapter, but I wouldn't worry about it too much. Okay, let's go back and focus to the alpha, beta, and delta cells. So Glucagon and insulin, you might have heard of insulin with diabetes and diabetic patients. And these two hormones are going to work opposite of each other. So insulin is going to be released whenever we have a bunch of glucose in the bloodstream, versus glucagon is going to be released whenever we don't have a bunch of glucose released into the bloodstream. So they're going to balance each other out, and they'll always be on in some quantities, but one will definitely be in a greater quantity than the other. And it's really important to understand that the beta cells are the ones that are releasing insulin, and then the alpha cells are the ones that are releasing glucagon. And if we actually look at what this looks like on a histology slide, we can see the pancreatic islet outlined here in the dashed line. We can see that it's a lot lighter than the rest of the ACE&R or the pancreatic cells surrounding it. And we won't ask you to be able to identify the difference between alpha, beta, and delta from a histology slide, just more conceptually which one is releasing what and when. Let's talk a little bit more about how insulin and glucagon are working together. So first, insulin. So insulin, when it's turned on, is going to be released whenever there's a bunch of glucose in the bloodstream. So this is typically going to happen just after you have eaten something, right? Because you've just eaten a good meal, and the nutrients are floating around in your bloodstream, which includes glucose, and now glucose needs a place to go. So insulin is going to go and try to grab that glucose in the bloodstream and either bring it in for storage or bring it in for long-term storage so that you can use it later if you need to. So what do I mean by bring it in? Well, glucose can't just float around on its own and just sit there. It has to be stored in a bigger form called glycogen. And glycogen is a bigger structure of glucose. So if you put a bunch of glucoses together, we would call that glycogen. And glycogen is really important because glycogen can be broken down by another set of enzymes and whenever we need to have an energy store. So imagine if you're running around in the woods and you get lost for 5 days, right? At some point, you're going to need to use your reserves of glucose, and those reserves of glucose will be in glycogen. So you'll break down glycogen to get glucose back into the bloodstream. So insulin will hold on to that glucose after a meal so you can have it stored in case you need it for later. And insulin doesn't work on every single tissue. It only works on the brain, the kidneys, the digestive tract, and insulin will, I'm thinking about something else. I'm sorry. So insulin will work on most different types of tissue cells in order to help bring in glucose into those tissues. So the ones that we mostly care about are the skeletal muscle, adipose tissue, liver, and the brain. And this is where we'll be able to store glucose as glycogen. And insulin can... insulin can bring in glucose into most cells with insulin receptors, but sometimes glucose can be brought in with insulin without needing a receptor specifically. So that's the difference between those two different bullet points there. All right, glucagon, on the other hand, is going to be released whenever we have a large amount of, or we don't have any glucose in the bloodstream, and instead we need to access our glucose reserves, so we need to break down glycogen. And when we break down glycogen, we call this glycogenolysis. So glycogen breakdown, glycogenolysis. And glucagon doesn't work on all of the tissues that insulin can work on. Glucagon actually can only work on liver and adipose tissue. It can't work on skeletal muscle tissue. That's a different set of enzymes and hormones that we don't talk about in this course. So glucagon can go to the liver and the adipose tissue and initiate glycogenolysis to break down glycogen so that we can use those glycogen stores to pull out glucose from those glycogen stores and use it as energy. So why do we care? Well, things can go wrong, and that the classic example is when insulin has some issues. So when insulin, for whatever reason, isn't working. We call this diabetes mellitus. And this actually translates directly to sweet pea. Right? Yeah, sweet pea. So back in the day, whenever someone would come to the doctor and complain of their urine smelling interestingly, or not normal, the doctor would actually taste test the urine, and if the urine was sweet, then they would diagnose the patient with diabetes mellitus, which literally translates to sweet urine. And gross, right? But they weren't wrong. For whatever reason, there was so much glucose in the blood, and the glucose wasn't getting stored appropriately with the help of insulin. So instead, when it was getting filtered through the kidneys, there was just too much glucose, so it got filtered out through with the urine. And this method is not used today anymore, and we understand a lot more about diabetes, luckily. So we don't need to taste test any more urine. But we actually are way ahead of what our textbook actually presents with diabetes mellitus. There's a lot more information on diabetes. But let's start with the basics. So there's two types of diabetes, type 1 and type 2. The difference between type 1 and type 2 is essentially what's happening with insulin. So type 1 means that insulin is not being produced in an adequate amount like it normally would have been. So there's glucose floating around, but we don't have enough insulin to hold on to glucose and bring it in the tissues. So we still have a bunch of glucose floating around in the bloodstream, and then it ends up trying to be filtered by the kidneys, and it can't, so then it ends up in the urine. Type 2 is different. Type 2 means that we have enough insulin floating around in the blood, but for whatever reason, whenever insulin grabs onto glucose and tries to bind to an insulin receptor to bring it into that cell for storage, it fails. That receptor doesn't work. So the same problem, except for a different reason. So we still have a bunch of glucose floating around in the blood, but for whatever reason, we can't bring it into the cell because of that receptor. So again, the glucose tries to be filtered out by the kidneys, but can't, ends up in the urine. So there's lots of different types of diabetes. There's type 1 adult onset, type 2 adult onset, type 1 juvenile onset, type 2 juvenile onset. There's even I can't remember what it's called, but mature juvenile diabetes, all sorts of different types of diabetes. And for the purposes of this class, we'll just focus on the basics of type 1 and type 2. But do know that there are a lot of different types of diabetes. A, for genetic reasons. B, for environmental causes. C, mainly diet-related issues. So if for whatever reason there is a lot of glucose in the blood all of the time and insulin is being overproduced, at some point the pancreas might shut down and not be able to produce enough insulin anymore. And so then you end up with type 1 diabetes. The difference between the adult onset and juvenile diabetes is either you had it over the age of 18 or you had it before you were 18. And we've even seen late juvenile onset diabetes. So in your early 20s, you have juvenile type diabetes, but even though you're an adult. So anyway, there's lots of different versions of this. If you're really interested in this, I'm happy to provide more information. Let me do a little bit more research because I'm not as up to speed on this as I used to be. So, but I'm happy to discuss. Here's a cute little meme. So pancreas, what happened to your beta cells? Don't you need those to make insulin? You are producing insulin, right? Oh, we have diabetes, don't we? So this should be an example of type 1 diabetes, right? Where the pancreas just isn't able to produce insulin anymore. All right, last but not least, all the extra bits. So the rest of your chapter goes through and says, hey, we have all these other hormones that are being produced by all these other tissues. You should know them. And that's definitely true. For instance, we've already gone through the heart and the thymus for chapters 20 and 19, but the rest of these we'll actually go through in depth whenever we get to, I don't know why the kidneys say see chapter 20, that should definitely be chapter 26. But whenever we get through chapters 24, 26, and 28, when we go through the digestive system and the reproductive system and the urinary system. And so here I just have the intestines and the hormones that they secrete, the kidneys, the hormones they secrete, the gonads, testes, ovaries, what they secrete, and adipose tissue, what it secretes. But we'll go over these in detail when we get to each of those chapters. Last but not least, we need to talk about homeostasis. So the whole point of the endocrine system is to maintain homeostasis. If something is out of balance, we need to bring it back into balance, mainly through negative feedback mechanisms. We can add some more terminology to this versus just negative and positive feedback mechanisms. We can say things like antagonistic and synergistic responses. So if we antagonize something, that means that we are opposing it, versus if we are synergizing with something, that means that we are working with it. So, for instance, those glucagon and insulin examples, those are antagonistic hormones, versus a synergistic example could be calcitriol and parathyroid hormone, where calcitriol gets turned on, then parathyroid hormone gets turned on. Versus calcitonin and parathyroid hormone, those are antagonistic hormones. We also can talk about permissive effects versus integrative effects. So permissive effects means that you need to have one hormone turned on before the other one can start working. So similar to calcitriol, but that's not always the case for calcitriol and parathyroid hormone. We can also talk about integrative effects or complementary effects. So for instance, did we talk about any examples? I'm struggling to think of an example specific from this chapter. But this is where you would have one hormone paired with another hormone and they're both doing the same thing. And maybe when they're both there together, they amplify the signal. When we're talking about growth, we're talking about growth hormone and thyroid hormone. For growth hormone, whenever we're thinking about that, we usually are comparing and contrasting children versus adults. So in children, we really want to promote growth and glucose metabolism, and it might actually be much quicker than in adults, but in adults, we still care about glucose metabolism because we need to mobilize glucose in order to make ATP so that the rest of the cells can function. Thyroid hormone, this is mainly for metabolism as well, and if for whatever reason it's not working, we might actually delay different systems from being able to function appropriately. Insulin is important for growth as well because we need to bring in glucose into the cells. So again, we can use glucose for cellular respiration so we can make ATP. Parathyroid hormone and calcitriol, if we don't have a mechanism to bring in calcium into the bones, we might develop a disease called rickets. Rickets was actually seen primarily in sailors whenever they were I can't remember what year, but all these sailors were having really weak and brittle bones to a point where they were literally just breaking with their regular weight put on them, and that's because they didn't have enough calcium in their diet. The reproductive system is also really important for growth, or related to growth, because if we're not able to grow those sex cells and we're not able to provide a mechanism for them to be supported while they're growing and maybe potentially during a fertilization, then it's not going to work the way they're supposed to. We also talk about stress. Stress is really relative to mainly the adrenal glands producing calcitriol, and in the cortex and in the medulla producing epinephrine and norepinephrine. And the adrenal gland is normally what we refer to for stress. And when we stimulate a stressful response for whatever reason, it can be short-term and short-lived. So let's say someone jumped out and scared you from behind the door, right? That's a short response. You'll immediately, your heart will race, you'll maybe potentially start to sweat. You'll completely forget you had an urge to pee or to poop. Your reproductive organs will take a pause, and your brain will be very focused and alert all sensation towards the potential threat in that moment, right? So that's the alarm phase, right, where you just got startled. But what happens if you were startled all the time for a really long period of time? Now we're going into something called long-term stress. And this can be really detrimental for a bunch of different tissues in the body. And let's give an example. So if you're taking an exam and you're stressed. The exam might be 2 hours long, so that would still be considered short-term stress. But imagine that not only is that exam stressing you out, but maybe your family's also stressing you out, your job is also stressing you out, you're not able to sleep and that's stressing you out. Maybe you have financial troubles and that's also stressing you out. Maybe your children are doing things and that's stressing you out. Maybe your dog is sick and that's stressing you out, right? So now you're stressed all of the time. Now you're stressed about something all of the time. And now that's turning into a long-term type of stress. So at some point, your body has to try to fight off this stress and reduce the amount of cortisol that is, or it won't be able to produce the amount of cortisol in order to negate that amount of stress. And this is when we get into the resistance phase, where your body is constantly trying to defeat the stress, but is unable to because you're just not able to make enough cortisol to diminish the stressful response. And if you do this over a really long period of time, like months, years, all day, every day, now you go into the exhaustion phase. And now cortisol isn't even able to be released at all in order to help defeat the stress. And so now other body systems starts to get affected, like the pineal gland. Your sleep-wake cycles are going to be affected. Your insulin levels might be affected. You might have glucose floating around in the blood all of the time. You might not be able to metabolize glucose as well, so you might be holding on to it too much. And whenever you have a lot of glucose needing to be stored, it'll be stored in the lipids and in the fat tissue. And so now you start getting now you start gaining weight, and then that's going to additionally stress you out because now you have to think about losing the weight, and so on and so forth and so on. And then if you're carrying too much weight, that could put a lot of stress on your heart. And then if you put a lot of stress on your heart, that could put a lot of stress on the rest of your muscular system, and so on and so on and so on. So that's when we start to get to that exhaustion phase. So our bodies were designed to deal with stress in the short term, right? We were hunters and gatherers. We saw a bear, we ran away from the bear, but then we were able to move away from the bear and be fine. We gave birth, but then birth was done, and then the village helped take care of the child, right? So short-term stresses, not prolonged long-term stresses. And so now this is why we name this the general adaptation syndrome, because over time our society has kind of evolved us to live in the resistance and exhaustion phase all of the time. And so that has had a lot of downstream effects for our physiology. Okay, moving on. Behavior is also really important when it comes to hormones. If we start activating the reproductive related hormones at an earlier time, this can change our brain chemistry, and depending on what types of hormones are being released and when, they might be more, or those children might be more susceptible to be sexually active at earlier ages, or they might be more or less aggressive depending on what hormones are being released. It can also affect memory, learning, and emotional stress. So we just talked about, emotional states. So for memory and learning, if we are affecting the brain chemistry, so we don't have enough glucose being stored for our brain to use that as energy, we might have difficulty remembering things or making new pathways in the brain. Emotional stress as well. So the hypothalamus is responsible for general homeostasis, for like body temperature, hunger, thirst, etc. But the hypothalamus is also responsible for sex, and it's right next to the amygdala, or it directly talks to the amygdala, and the amygdala is responsible for our emotions. So if the hypothalamus is unhappy, the amygdala might be unhappy. It all relates to everything else. That's the whole point of this slide. Same thing for aging. So eventually growth hormone starts to slow down. We won't be able to produce it as much. Insulin might not be able to work as well anymore / at all. And our adrenal glands might not be able to make cortisol like they used to, so we may not be able to respond to stress as well. We might not be able to make might not be able to make aldosterone as well either, which means that we'll have a harder time increasing our blood pressure when we need to, and so on and so forth and so on. So here's the picture at the end of the book that always talks about homeostasis and the capacity for that chapter. I highly encourage you to take a look at this and be familiar with how it relates to each of the individual systems. And if you have questions, go back to each of those systems and kind of review those processes. I'm happy to talk about it more one-on-one if you have questions. But especially for this chapter, homeostasis is the name of the game, so please be familiar. And as always, you have those review questions at the end for extra practice. I'll see you for the next one.